in this lecture we will talk about the natural weighted regression. First of all, I would like to emphasize what's the natural weighted regression. This comes from the Gaussian natural curve, or you can say it is also known as bell curve. First of all, what is the Gaussian net? Okay, let's talk about the natural. Natural means, for example, if it is raining somewhere, so rain is pouring, its drops, rain droplets comes naturally. Or okay, let me make it very simple. For example, somewhere there is a entry test to enter in the medical exam or just after schooling. Some students who passed FSC or OA level and appeared in the MDCAT. If I am talking about the only KPK region, Khyber Pakhtunkhwa region, where usually more than, you can say, 20,000 students appeared in MDCAT test. So in this 20,000 students, let's suppose they need to appear for MDCAT test. The total marks of test are 800. So let's make a natural graph how these students are behaving naturally by appearing in this MDCAT test. Suppose this one represent number of students. This one is the, you can say, score. This represent 100, 200, 300, 400, 500, 600, 700, 800. So these are the scores. Let's check out how many students out of the 20,000. Okay, suppose there are 2,000, 4,000. Okay, even number, kind of 20,000, 18,000, 16,000. So evenly, each jump is just after 2,000. So suppose there are few students, who are getting less than, there is suppose 0. For example, few students will not appear in an entry test, are getting 0 score. And some students who did not prepare well, or maybe due to certain sickness, are getting very low score, or you can say kind of 100 score. And some students will get, they are very low grade, they did not prepare well, or they don't know too many, their background knowledge is not up to the mark, and they are getting some 200 out of 800. Some students who are getting better than this, but they did not prepare well, their knowledge is not up to the mark, you can say this one. some students who are, you can say, prepared but average minded, or you can say not very well prepared or not very much hardworking students. They are abundant in number, too much numbers. Okay, so kind of this, and then some students who are preparing well and getting a little bit good score. Then again some students who are better than these and they are preparing the contents nicely, and some students who are also achieving the very good grades in class and with a little bit outperformance, and some students who are performing extra outstanding, or who are performing very well, very well. So these are very less in numbers. So if we are connecting all these points together, we will get a curve like a bell shape. This bell shape curve represents that only few students who are getting almost 0, maybe they do not appear in a class, and only few students who are getting 800 out of 800. But students who are getting 400 out of 800 are too much, or you can say they are average in number. These are the, you can say, at the maximum point. So this is the mean position. This is the mean position. So this distribution, okay, around, or you can say about the average, is known as natural distribution, or you can say natural distribution, or you can say Gaussian natural curve. So the formula for this is representing, with the help of formula for this function, is representing some kind of error term, pi. This is the sigma, and you can say here some clear space. So you can say some error term, function of error term, and 1/2 pi, because it is along the line. So, and the bandwidth, this is the sigma from this point, okay, this is the sigma from the mean position to the maximum edge, or you can say bandwidth. And here this is representing with exponent and negative sign. I will explain it a little later. So you can say y minus r here. Error term divided by 2 sigma square, this error term square. So this is the formula where error terms represent the given value, difference between given value or the hypothesis value or estimated value. So this here, this sigma represents the bandwidth from this mean, this, okay, from the mean position to the one edge, maybe this side, both sides. So error okay, for example, there is some value, some students are attending the number here, but the given data, or you can say this one is the given and this one is the actual, so difference between this is some kind of a error term along this peak, along this bell curve, and this one is the hypothesis. Okay, this one is the, you can say this one is the hypothesis, and this one is the y given value. Make it more. This one is the given value, and this one is the hypothesis. This one is the hypothesis. So difference between these basically these are 2 points, not a line, but 10 lines. So we need to, with the help of this function, Gaussian natural curve, we are predicting what is going on or what kind of error is there. So in this natural weighted regression, we will use this Gaussian bell curve formulae. For this, let me explain, such that our weight parameter to fit the bell curve for minimizing the error. And this minimization of the error such that is also kind of a distance. This thing. So let me explain, and we will consider this weighted, okay, this weighted natural we will consider this natural weighted regression with some weight parameter Wi. For I is representing for number of examples, for number of experiences we are doing, with some E, and of course this is nothing else except some observation. We are visiting, in case of houses, we are visiting to the number of houses, and this one is the benchmark house for reference purpose, with some scale, this term, and if, okay, here, this one is some kind of a error term, this one is some kind of a error term, we say if difference between this observed value and the benchmark reference value is very, okay, you can say small, then we can say weight equivalent to 1. Something approximately equivalent to 1. Why? Correlation. That it is fine. That almost both this benchmark and the observed value is almost similar. So difference is small. Okay, very less. So we will say this is equivalent to 1 if observed value and the given value difference is very large, then no relation, okay, totally different things. So this is different thing, this is different thing. Then we will say this weighted, then Wi, locally weighted regression, this weighted value will almost equivalent to 0. So our error term for each number of examples can be followed natural distribution such that our hypothesis value as well as to the bandwidth. This bandwidth basically that how we are far away from the original, from the center. Okay, how we are far away from the center, far away from the center. This is representing with some sigma. So this is this error. If we are very far away from the given value, then of course the problem is too high. So hypothesis value, okay, we need to consider some kind of an average result for better accuracy and better precision. So let me explain further how we will consider it. Here we need to consider some kind of probability, that what are the chances of this error follow an equation of, this is the Gaussian, okay, so that here I will explain this exponent, what is the exponential term, sum of like this, square divided by 2 sigma square, where we can further expand it 1/2 pi sigma exponential value and negative. So here yi, the given, okay, data, given values, and this one is the hypothesis. This is, I am writing the roughly, okay, equivalent of the error terms in the denominator to sigma square. This is the, here this probability, this error, we are basically parameterize the error such that P for given y such that x number of example parameterized by theta weight value. So this is the probability for given with respect to the its number of example, and also depend upon the parameterized by the weight value. So we will need to solve this because we need to get a probability of the chances such that, remember, this error term or IID, this IID representing independent identical distribution. So what is this mean? Every error, okay, it is, of course, we are if we are talking about each student, all of you are varying, okay, if we are talking about some person, each person is varying from, okay, if we are considering the concept of life is varying from person to person. The meaning of life is different from for every person. So independent, and of course each one is having unique potential or unique problems, unique mindset, but the traits of humans are identical. To notice the thing, personality traits are independent, but moving, behaving, for example, if we are seeing some kind of a fire alarm, every one of us are some kind of getting scared. So this is identical. So we need to get the likelihood that how one person is similar to another, or how the traits of one person is likelihood. One person is likelihood to another person. You need to check out the dictionary meaning of likelihood. You will see there's some kind of similarity trait. Okay, so likelihood of this probability, or you can say chances. As we are talking about machines are mimicking the human brains. So how much likelihood that machine is behaving similar like a human? So we need to perform some kind of a likelihood operation, and of course it's a weight parameter. Such that you can say it's if there are too many events, in case of likelihood, we are considering the product of all the events. So there are m number of, we are observing m number of examples. Product means that, okay, we are multiplying 1, 2, 3. So 1, 2, all numbers are different, so we are getting the product of it. This is for getting their likelihood that how much, if we are multiplying 1 into 1, it is exactly similar. We are getting the dot product. So you need to study the concept of dot product. You will see why we are using in the product in likelihood. So likelihood, we are considering the product such that we need to parameterize some given value of y with respect to the feature values parameterized by the theta. So in this situation, we need to expand this, and we know this is what? This is follow the Gaussian natural curve. Okay, so locally weighted regression. We need, let me derive this. It is very beautiful. So with the concept of probability, if we are talking about the probability, or for example in case of the we are tossing some coin, so head plus tail give us the maximum, okay, probability equivalent to 1. How? If we are tossing some coin, we will get chances of the head out of the two possible value, head and tail, that is 1 out of 2. So here, if we are talking about the chances of getting tail out of two possible head and tail, it's a 1 out of 2. So we will see maximum equivalent to 1. So here, in classification case, we want that this output give us 0 or 1. That is also kind of a binary situation. So in probability situation, we will this 1 over 2 plus 1 over 2 equivalent to 1. can be written as probability of y equivalent to 0 if we are talking about the, okay, let's talking about the head. If we are talking about the head, so equal to 1 such that x is parameterized by some theta value. This is the chances once we are getting head. The chances we are getting tail, probability backside, so y equivalent to 0 such that x is parameterized by theta weight value, so total equivalent to 1. This is what, for example, this is telling us in case of classification that one is some kind of a malignant tumor. So if we want to know how much it is malignant, then we will notice that P y equal to 1 such that this value, okay, this is benign, will be subtracted from the maximum value 1 minus y equal to 0 x parameterized by theta. So this is a beautiful concept of the probability, that whatever this is the threshold value, automatically will be configured from the maximum, okay. This benign will be subtracted away and remaining we will get the malignant one, dangerous one. So in terms of how we can write this equation in this benign and malignant, okay, the classification of two possible outcomes in a compact way with the help of beautiful concept of probability, such that parameterized by theta can be written like this is the sigmoid function. Remember, this is the sigmoid function. I suppose it's with x, and here y. Okay, I'll explain it. And what else? 1 minus g of x and 1 minus y. This is a trick. Okay, let me make it replace the, okay, in case of sigmoid function, this we will consider the hypothesis value z, because z is somehow our such value for what we are talking about z such that z equivalent to theta transpose x. Okay, so we will substitute in sigmoid function. Which sigmoid function? This sigmoid function g of z equal to 1 over 1 plus e minus z, and once we will get the value of g of z, we will substitute here, and this is basically what? Probability. How? If we are considering in this equation, if we are considering y equal to 1, then here it will give us 1, and this y, of course 1, it will become 0, the power in this whole will become 1, and we will get the probability y1 equivalent to what? This g of z. There is no need to write y here, y equal to 1, just ignore, okay? Just only this answer we will get. Simple sigmoid function. If it is a malignant. If it is a benign, what will happen? P y equal to 0. So once there in this equation we are substituting 0 at this position, then this whole will become equivalent to 1, and this will become 1 minus g of z, because this 1 minus 0 equal to 1, So we will get 1 minus g of z. So this sigmoid function will be subtracted away from the maximum value. So you will get the remaining benign output. This is the beautiful concept. So how this beautiful concept work out? By using the maximization of likelihood such that L of theta. So we want to maximize it by taking the log value of our likelihood. So here, once we are getting this likelihood is what? This likelihood basically equivalent to this one. We need to substitute the value this value. So log we will say here g of z, okay, here y, and 1 minus g of z, 1 minus y, and oh sorry, here I need to mention this, okay, log this product, and once we will expand it, this product will transform into the summation, and we will get y log g of z, and this power due to log plus sign, okay, this product will transform into the summation. So we will get some kind of a special. So here we will get, we can consider here, okay, what's this? Summation, and we will get here 1 minus and this is showing some kind of 1 minus y log 1 minus g of z, this one. So this is your required, okay, maximization of likelihood. Once you will consider this y equivalent to 0, okay, we are talking about the benign thing, then this term will become 0 and this term you will get in remaining, and this whole term. So this term, you will get this term, and this term will be used further in the estimation of weight parameter theta, such that theta plus this step function, I will explain this step function further, okay, gradient descent of this maximization of likelihood theta, or this one, this, okay, you need to consider this one, some kind of partial derivative with respect to theta, likelihood. So you will get some kind of a summation y minus g of z. This is your estimation value. You need to get the partial derivative of this with respect to theta, and this is somehow your cost function j of theta equivalent to 1 if we are talking about for and number of examples. So you need to get this cost function. And this cost function will help you out to predict the possible probability by considering y equal to 1 for fixing number, so parameterized by theta plus probability y equal to 0